Yeah, good morning. So today we are going to continue with our forced response vibrational analysis or forced response vibration study of a system for harmonic excitation. We are going to continue with what we were doing in the last class. I'm going to share my Active Inspire board and quickly let us review what we did in the last class. And we're going to add today an important part of the lecture. So let me share my screen. In the last class, essentially, we were doing response of an underdamped system for a harmonic force excitation, right? So that's what you are able to see here in this spring mass damper system. It's been excited by external force F of t is equal to F naught cos omega t from its static equilibrium position. So there is an impressed or an external excitation force that is continuously acting with an excitation frequency omega. Then you would have the response, what is called the forced vibration response. It is not like disturbing the mass from its static equilibrium position, either by giving some initial displacement or initial velocity and leaving it to absorb. That is what is called a free vibrational response. And you are able to differentiate that clearly. What do you mean by free vibration? What do you mean by forced vibration? So this last class, we just learned a forced vibration study for a harmonic excitation to the vibratory system. The elements are mass, spring, and damper. And the damping here is under damped system. The zeta value is less than 1. Is what is referring to underdamped system where you will have an harmonic oscillation. Whereas if the zeta value is 1 or greater than 1, you know it's aperiodic, you will not have a vibratory system. So this background of significance of damping in the system, and because damping present in the system is not conservative, there is a damping force, and that force is what is dissipating energy in the form of heat or sound in the vibratory system. So this is all that background you know, and we were just looking at the amplitude and phase is given by this expression can be derived and can also be easily remembered from its vector diagram representation, right? And we were having importantly defined what is called the magnification factor, and that was expressed in terms of non-dimensional ratios. It is essentially defined as the ratio of dynamic displacement to that of static displacement of the vibratory system. When zeta value is 0 here, that is going to give you an analogous study of free vibrational, free forced, sorry, not free, undamped forced vibrational magnification factor. And any time you see for such kind of governing equation of forced response or forced response vibration would have two part of solution. One is called complementary part, another one is called the particular integral part. So the complementary part is going to die out. There is a shortest settling time, and this part would go. After that, you will have your response is either in phase of excitation frequency, excitation force, or out of phase of excitation force. It depends upon the phase angle, or it depends upon what is the excitation frequency compared to that of its natural frequency. This is all something that we have already learned. And the characterization of your magnification factor and phase angle, which is function of the frequency ratio. So what is the frequency ratio we define here? Is ratio of frequency of external excitation force to that of natural frequency of the system. So this ratio is going to influence this magnification factor and phase angle. So this is also in detail that we have discussed in the last class. And then we were looking at importantly the representation of this entire thing with an vectorial diagram, and that is giving you easily to remember important things such as like this. So I can look at here to say that what is my phi. So this phi would be tan inverse of opposite side is c omega x by adjacent side. So C omega x by, this is kx minus, so this side would be kx minus this. So kx minus m omega square x. So this x is common, that goes. So you would have, this is tan inverse of C omega by k minus m omega square. M omega square. So this is how you can remember what is phase angle, and you know what is your F naught magnitude. So the F naught would be under root of kx square, kx minus m omega squared x whole square plus c omega x whole square by Pythagoras theorem, because this is 90 degrees. So you would be able to represent from this only. Your x is taken out, and this is going to be under this radicals. So this is what is F naught, and here is where we have defined x by delta st is nothing but F naught. But F naught by kx is what is taken down. So this is 1 by under root of the square plus the square. So this is how you can always remember. Vector representation is always quite useful. And this is what we have seen. And finally, and finally, we were looking at, importantly, what is this maximum value of this magnification factor, right? So you can see that it's clearly from characteristics of this variation of this MF with ratio, this peak value is not exactly equal to 1. It is slightly skewed on the left, lower than 1, and that value to obtain, we were taking this magnification factor, which is function of this frequency ratio. So differentiate and equate to 0, you get the value corresponding to the maximum value, and we were doing that. So with that, we ended in the last class. And today we are going to learn again a force response study to understand what do you mean by displacement transmissibility. So for that, I'm going to teach you today the response of damped system under harmonic motion of the base, right? So this is lecture number 10, and today's date is 25/08/2021. And what is that we are going to do is force response study for harmonic base excitation. For harmonic base excitation, we are going to look at what is its response. So how do I look at now? So for the mass was hung, instead now I'm going to have the mass which is supported by the spring and damper, and I have this base. This base. If this base is given an excitation, that is the displacement. Say this is y of t is equal to y sine omega t, and this is, if I have function of time, I will have the excitation of the base is given by this. So if I give like this base is exciting like that. Now the mass is going to have its response from its static equilibrium position always. So when there is no excitation, the mass sitting on it all set in its static equilibrium position, and then it will go and have its x of t response. So this mass, stiffness and damping, and this is your base. So in the earlier case, we don't look at excitation from base. It was excitation given to the mass itself. So there is no motion of this base. So if we have understood this, this is going to be analogous to looking at vehicle going on a road surface which is having sinusoidal profile. So the vehicle durability test would be conducted in a vehicle manufacturer in the test track. You have a special road where the road surface won't be flat, it will be sinusoidal wave. So there will be a profiled wave road surface on which the vehicle will be ridden. At that time, you see the base is going to give an excitation that would be represented by y sine omega t. So then your mass of the vehicle, that mass we call it an unsprung mass. An unsprung mass is something which is constituting the mass of your tire wheel assembly. Anything below suspension masses, all are called unsprung mass. Body mass and cavity inside passenger all seated together in a vehicle, that is sprung mass. So if we assume that this mass now is a car mass, the body mass, and then these are all representing equivalent spring and damping values here of the suspension of the vehicle, you can just see that the vibration of the vertical vibration of your vehicle for a road surface which is of sinusoidal profile like this. That is what is that would be analogous. Today what you learn can be applied onto such problem. So now what would be the governing equation? So let me just draw free body diagram, and that would be equal to its kinetic diagram. So the free body diagram is from its static equilibrium position. So I would have the spring and damper. So the spring force is going to be, now it's not kx, it is going to be, there is a motion x and there is a motion from on the base also. So there is a relative motion. So the net displacement or elongation in the spring is x minus y. So k into x minus y and the c into x dot minus y dot. So what is x dot and y dot? So when the dash part, the ends of the dash part, upper and bottom, one is connected to mass, another one is connected to base or road surface. So there is a relative velocity, and that would be causing this force. And this is what is going to be equal to mx double dot. And considering this is positive upward, I would be able to write this equation minus k into x minus y minus, it's not plus, that's minus c into x dot minus y dot, that's equal to mx double dot. So bringing these terms on the other side, I would have mx double dot plus c into x dot minus y dot plus k into x minus y equals 0. So you should not think that why this 0, is it free vibration? No, I have my forcing, the excitation comes from the base. So what is that excitation that comes from the base is what is equivalent to the dot on external force that we have seen in the previous case. So for that, let me again simplify this equation, mx double dot plus cx dot plus kx. And I have minus cy dot and minus ky. So that I'm going to take it on the other side. So it's going to be ky plus cy dot. So this is my governing equation. So you see this ky plus cy dot is what is that comes from the road surface, and this is your external excitation called the base excitation to the vibratory system. So now let us understand this road is represented by y of y sine omega t. So if I substitute that in this, what is that I'm going to have? I will have, this is going to be k into capital Y sine omega t and plus c into y omega y cos omega t, because I substitute y dot would be differential of that, I substitute that, and now this can be rewritten as mx double dot plus cx dot plus kx can be rewritten in another convenient form. So this is your governing equation now. So this side of that, I'm going to rewrite, instead of ky sine omega t plus c omega y cos omega t, I'm going to write this as, I'm going to write this as this. I'm going to replace this by an amplitude A time sine omega t plus alpha. Instead of writing it, mx double dot plus cx dot plus kx. So now here, what is this A is an amplitude. I'm writing this two one sine function and cosine function into combined form that we have seen. We are not new to this. We have already seen that in our previous classes. So I'm writing with this phase angle difference. So now, how do I represent? How do I understand this? That's simple, right? So how did you get this equation? Is from the trigonometric relationship. From the trigonometric relationship. So what is the trigonometric relationship we use for that? Sine A plus B is equal to sine A cos B plus cos A sine B. So if I use that, I would be able to deduce this form. So let me just explain you that, right? So how this comes, if you do, most of you would have understood, but still I would write here for your benefit. So you know sine A plus B formula is sine A cos B, sorry, cos B plus cos A sine B, right? So here, this you see here, sine omega t cos omega t is there. So how do I get this? I will represent now my A1 or here A. So this is, see here, this is one term and this is another term. So I'm going to replace this ky and cy like this. So this is going to be represented like this. Just written down somewhere. Yeah. It would be easier if I plot you the vector diagram. So let me just plot the vector diagram and then you'll understand. So this is, now I have my road profile, right? So road profile is y is equal to, this is omega t. So this is y, right? Just a minute. Yeah. And my, this is y. And this y is what road is attached to the mass through the spring. So I would have a spring force that I would just have it. So that would be from origin to this point, that is ky. And I would have correspondingly the force impressed by dash part, that is going to be c into y into omega. And I would just join this. So this is 90 degrees, and this is going to be now the amplitude in A. And this amplitude is what is equal to y into under root of k squared plus c omega whole square, right? So this is as far as the road excitation is concerned. So road excitation, since the road is the base is attached to the spring and damper, I will have force exerted on the base by this, and damper is this. So the resultant amplitude of that is given like this. And this is what is now at omega t plus alpha. So what is omega t now? This is omega t, and this angle is alpha. This angle is alpha. This angle is alpha. So the angle omega t plus alpha is this. This is omega t plus alpha is what is now the amplitude A, this vector A that is there here, and sine omega t plus alpha is what is going to be your impressed excitation due to road profile now. Now my response would be thought of like this. So x of t for this, what is my response? And the response would be somewhat, it is in this way. So this is x. And since the spring is there, I will have kx. And then I would have this is c, this is c omega x. And you see this difference here is what is m omega squared x, inertia force. And if I just project this onto this is 90 degree. So what do I have here is now is this. My response, let me write the response for this excitation, for this governing equation, the response x, steady state response, xp of t is going to be x sine omega t minus phi minus alpha. So this is that response. So if I solve this governing equation, substituting a trial function, a harmonic function, xp of t is this, and this would satisfy this equation. So this equation would satisfy my governing equation of damped vibration due to base excitation. So this all are captured in this vector diagram. That is what is an advantage of drawing vector diagram. The equation can be best understood. So now you see here omega t minus phi minus alpha is what. So what is phi here? It is the phase angle of response to that of an impressed force. So then what is here phi? The angle phi here is this angle. So this angle between A and X is what is phi. So you can see that omega t minus alpha minus phi is what is X. So this angle here, this is that angle here phi, our phase angle. So phase angle is what what is the phase difference between my response to that of an excitation? That is phase angle. So now this you can see omega t plus alpha, right, minus phi is what is going to be this. What is going to be my x? So this all have been captured. So this is my solution. This is the response for base excitation problem. If that is so, here you have to see now the phase angle here is not simply phi, it's phi minus alpha. So there is an alpha introduced here in order to handle this equation comfortably by means of this. And that is all are very clear only with this kind of vector diagram. So now, see how can you write this this all in this form is to use this. I leave it to you to look at it, and you don't get, I will explain later on. And that is clear here. So now what is this A? The amplitude A here from this diagram, you can say that it is under root of ky whole square plus c omega y whole square. That is A. And what is x here? The amplitude of response, this is x. So that x would be here given by y into under root of k square plus c omega whole square divided by under root of k minus m omega square whole square plus c omega whole square. That is x. And here, what is this angle alpha? Alpha is, look at this diagram, alpha is here, there is a right angle here. So that's tan inverse of opposite side is c omega y, adjacent side ky. So y goes at c omega by k. That is alpha. What is phi angle? Tan inverse of this angle phi. So opposite side is this. So this is what c omega x. So c omega x by adjacent side is kx minus m omega squared x. Kx minus m omega squared x. So in this also you have this x that goes off. So I would have It's tan inverse of C omega by K minus M omega square, right? That is fine. But now, what is the phase lag than from the excitation is this. So phi minus alpha is my phase. Phi minus alpha is my actual phase difference for my excitation. So excitation is what? Y of t is equal to y sine omega t, and response is what? X of t, that is x sine omega t minus phi minus alpha. So this is what is now collectively is called the phase difference between excitation and the response, and that would be simply phi minus alpha. So you will have this difference. So tan inverse of, you will see this is quite useful in vehicle dynamics. You will be seeing this. Once again, we will revisit this, right? So tan inverse of C omega by K minus M omega square minus tan inverse of C omega by K. And we have already learnt beautifully, we can replace the explicit appearance of Kc, omega, Kc and mass. These three elements values can be removed from the system, can be replaced by introducing the concept of damping ratio and frequency ratio. So if you do that, what is my x value? My x value is going to be y into. So what I have to do for that, take amplitude and divide numerator and denominator by k. So k by k, multiply this by k. So that's going to be inside, that's 1 plus C omega by k whole square, that we have seen 2 zeta omega by omega n. So that's going to be that square divided by, and here when I introduce k inside, it's going to be 1 minus this, so 1 minus omega by omega n whole square into square. This is all under radical sign, plus C omega by k, that's again 2 zeta omega by omega n whole square. So that's my x. So the amplitude is now, see, that's difference. So magnification factor in the previous case you have seen, the numerator part here is brought down, and that was delta xt. But this was not there. That was only delta xt is brought down. So x by delta xt is what is 1 by this we had. But now you have this. So this is quite useful now to define what is called displacement transmissibility. That's called T subscript D. This ratio. So what is that? It's a dynamic amplitude response of my mass, my vehicle body in vertical direction to that of the amplitude of road profile or the base excitation. So base is moving like that. So I can have this fixed road wavy and then ride my vehicle. There I give my displacement of my road and then excite my vehicle in real time test. Or you can also have that vehicle seated on a laboratory on a 4-post hydraulic jack, and all the posts would go up and down with a sinusoidal wave, and that would be an excitation to your vehicle. And you consider the vehicle to be a single degree freedom system. Of course, it is a continuum system. We will discretize it and make it as a multi-degree freedom system and so on. That is for a detailed engineering analysis. But however, to understand an important rigid body mode of your vehicle called bounce mode, vehicle body going up and down in vertical direction, it is very good that we make an assumption of single degree freedom system. That is what we are discussing today. So this displacement transmissibility is important. So when I give Y amplitude harmonic excitation to my vehicle, I get X amplitude response of my vehicle body. So this ratio is what is called a displacement transmissibility. So if I give this and there is zero displacement, that is what is best vehicle. You would have 100% isolation that's possible in your vehicle, right? So what is preferred for your comfort? What is preferred for comfort? Comfort of a car, this x by y should be tending to 0. So when can it happen is what you'll understand in a while. And that would happen when omega value is much, much greater than omega n. That means the natural frequency of your system is there. Your vehicle vertical natural frequency sprung mass is there. So I would give you that value around 1 hertz for any vehicle design. So if you look at that, would be around 1.05 like that. That is the frequency. And you see your road excitations are in higher frequencies, say 1000 hertz, 2000 hertz, road profile. It's very smooth road, asphalt road. You would see absolutely there is no bounce in your vehicle. But the endurance test, durability test of your vehicle is tested that you have to go over a bump of your correct? A speed breaker. So that speed breaker, when you go over, that's kind of a large cleat and it would excite a strong impulse. But if that is continuously made on a road, you see your vehicle would be always going to have excitation in a sinusoidal wave, and such kind of test tracks, patches are there. Any vehicle would be tested for its endurance and durability. That vehicle, nothing would happen to the parts. So you would severely run it on a sinusoidal road, and you see what is the amplitude. So that amplitude, when you go very slowly, see your vehicle speed is not excitation. Your vehicle speed, the road texture is what is your excitation here. So your road texture is what is your excitation, that if you see, and you would have this x by y value going to 0 is preferred for comfort study, and this would be equal to 1 when it is very, very small. So that's what we'll see. So what is that is going to be now? This ratio, it's going to be 1 plus 2 zeta omega by omega n, omega n whole square by under root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. So you can see in textbook this omega by omega n is referred by R. So if we refer R as frequency ratio omega by omega n, this equation can be simply can be written in a compact form. You have to rewrite this equation many times in your paper notebook so that you would be very comfortable. So this is your displacement transmissibility. And what is the phase difference? Phi minus alpha, that's going to be tan inverse of this by this. So 2 zeta r by 1 minus r square minus tan inverse of 2 zeta r by 1. So that's 2 zeta r itself. So this is what is your steady state response if your vehicle is excited by the road sinusoidal profile. Any doubt in this part? If you have, please ask. Otherwise, we'll continue. So what is that I was telling? For that, I just had this picture for you. You can just go through. Before that.
So can you show the other slide for a second, sir?
Yeah, just this one, right?
Sir, little more. Yeah, yes, sir. Thank you, sir.
Yeah, please note down. Is that clear? Are you following what am I explaining you? So we are not now independently doing mechanical vibration. Why do we study mechanical vibration? Is to understand vehicle dynamics, particularly vertical dynamics of your vehicle dynamics part. So that's nothing but mathematical modeling of your vehicle with the spring damper mass system. So the simplest vehicle vertical dynamic model, ride comfort model is single degree freedom model. What is that today you are looking at with this kind of equation and physical elements and the response. So let's now going to have understanding of how this displacement transmissibility and this phase angle is going to be varying as function of frequency ratio, like in the last class we have studied, right? So that's what I'm going to explain you in a while. So this is what in the last class that we were doing it. You remember? This is not for this. So what is this diagram? This is for harmonic excitation. This is for harmonic excitation of f of t is equal to f naught cos omega t or f naught sin omega t, right? So if we have this and we have magnification factor, last class we have looked at, you would have when zeta value is 0, this magnification factor at ratio 1 is going to go to infinity. I just have put this diagram from the textbook so that you would have a clarity. We had the same discussed in the last class. Here you would see. So this is the plot. So here these curves are smooth curves. I have not drawn very smooth, and this variation. So we have gradually plotted and we have understood this nicely. And the whole sum of that is what is this? Once again, I have put so that you can see for this particular case, right? For this particular case, once again. So anything below 0.707, you do not have a peak. So this all goes like this. All goes to 0. Someone was asking it all to go to 1. It is not so. That is a special case, different case, right? So this all goes here. And you see, irrespective of the damping, you see as omega is much greater than omega n, it reaches to 0. Magnification factor reaches to 0. And it starts at the 0 frequency excitation from 1. And in this zone near to 1, you have completely it is governed by damping present in the system. So the moment you see the damping present, it will bring down your amplitude. And this amplitude peaks here are skewed to this value of 1. And that's what is the reason why a peak amplitude or peak frequency that you're seeing, right? So peak frequency omega p is given by omega n into 1 minus 2 zeta square. We have derived this expression. We should not get confused with the omega d, natural damped frequency, damped natural frequency, that is given by under root of 1 minus zeta square. So there is 2 factor here, remember. So because of that, you see this omega p is not equal to omega n, and it's smaller than that, So omega p is smaller than omega n. And that is the reason why you get your peak corresponding to substituting this back, you get it here. So this is all we discussed. And on the phase, you look at, irrespective of the damping value, you see that the phase angle 90 degrees at that time, they all have at frequency ratio when at resonance state, omega is equal to omega n, that's r is equal to 1. At resonance, whatever may be your damping in the system, you have phase angle 90 degrees. And that is what we have understood nicely in the last class, looking at this again vector diagram. So at resonance, you see that your force balance of damping force by external force, and the spring is nothing to do with that, and spring balances your inertia. So the complete governance is only by c omega x, and the phase angle is 90 degrees. So this is what is to be remembered here. And as the damping value varies, as you see here, it is increasing damping value in this way, right? This way. So this is 5, 1, zeta 0.5, like that, right? So you have, so all are going 180 degrees asymptotically longer. So when the damping value is very small, then it would quickly go to this. When damping value is more, less than 1, it will take some time. So this is that the characteristics of magnification factor and phase angle that we have seen. But now for today's case, you will have, instead of magnification factor here, you will have x by y, that is displacement transmissibility. And how does it vary, we are going to look at. And instead of phase angle phi here, see, this is a different case. Now what is the phase angle? It is phase angle of my response to my road excitation. Y is equal to y sine of omega t. So that angle is phi minus alpha, and we have defined alpha there nicely, right? So how does it going to vary? That's what I'm going to explain you in the next slide. I take that slide straight away. The response. So this is what is that I was telling you. So the response of a damped system under harmonic motion of the base. So look at this road, it's so this wavy. So you have this vehicle is going on this kind of sine wave. So this can be imagined as y is equal to y sine omega t. So where this omega is the frequency of this road profile, and t is at any time your y value in this. So when vehicle goes over this can be modeled as sprung mass. Sprung mass is any mass above the axle, above the suspension. So the tire wheel mass, all called unsprung mass, can be neglected when you compare this mass value compared to the total vehicle of this total mass of the vehicle body. So this is your sprung mass, and you have your equivalent front axle, rear axle suspension, equivalent stiffness and equivalent damping value, and that is what is now on a sinusoidal road profile like this. So this is y is equal to y sine omega t, and this is going to be with the x of t. So this is how you can model this, and whatever that we have looked at today, the equations all holds good. And we will end our lecture now in another 5 minutes, understanding the variation of displacement transmissibility and the phase phi minus alpha of the system as a frequency ratio, right? So for that, let me take readily this graph, and you have this here. So look at, I think it is better to have the previous graph also here, so that you would be able to compare the difference and remember the things. Let me go back, take this as well. And look at that parallelly. Right. So look at that. In the last class, what we have seen, it was like this. Now, again, you see here, x by y, here, this displacement transmissibility, all starts from 1, like in this case. But you see here, this value of zeta here is 1, right? And zeta value, here you see the zeta value 1, below this we have seen 1. And here it is that the large one. And then you see 0.5, it is going like this, and 0.25, 0.2 zeta value, 0.1 and 0.05. So the amplitude is huge. It's 0, it is infinity, that is an ideal case. So you have your omega here much less than omega n below this, and here as it goes, it's omega much greater than omega n. So what is here, this omega? It is the frequency of base excitation or frequency of road profile. So you look at here, as the damping value increases, the amplitude of that is transmissibility, displacement transmissibility decreases. So when you have a zeta value much greater than omega n, that reaches to 0, that's where you get your x by y tending to 0 at this point. When omega value is very smaller than that of natural frequency, right, of the system. That is why when it is on a wavy road, you go with very slowly, right? Your excitation, your natural frequency is 1 hertz. Your profile is not equal to 1 hertz. It's smaller than 1 hertz. Then road profile is like that. You will have this one. That means whatever your x is there, that's going to be y. So your vehicle would embrace with the, means it will just go with the wave like that. So both amplitude would be same. There won't be any vehicle vehicle body also will have the same. So whatever the amplitude of road surface, the vehicle also will have that amplitude of vibration. Whereas in this case, the road is like that. When we go on that, the body will not have any displacement. That's interesting, right? When x is 0, that means what? This mass sitting on this. So this is the road. This is not transferring anything. There is no displacement. So this is x is equal to 0 here. It is in static equilibrium position itself. Whereas this is there, y is equal to y sine omega t is there. That can happen when this omega is much greater than omega n. So the sprung mass, natural omega, natural frequency of sprung mass is under root of k equivalent by ms. That will be equal to some value. So in hertz, it is 1 hertz. It is 1 hertz. So how do you get in hertz? So 2 pi fs is equal to omega ns. So fs is equal to 2 pi, sorry, omega ns by 2 pi. So omega ns here would be around 6 point something radians per second. Divide by this, you would have, this is 1 hertz. That's for taking any vehicle, its mass and the suspension thumb rule design. So it will be 1 hertz. So your excitation is much greater than 1 hertz. You would have that there's nothing would happen. What do you mean by excitation much greater than omega n? I have here my amplitude is seen here. This frequency here. This is my wavelength. So this wavelength is going to be very small. And amplitude I can have wavelength is very small, and then your frequency would increase. So the higher the frequency, you would have x value 0. That's why asphalt road, if you look at, there is no absolute view of profile, right? You can't see that profile. Looking at this picture in the previous slide, this picture, you can see that this is wavy. If this wave is instead of going like that, if this wave is very close waves like this, much close wave, what will happen? So many waves, it is going to be flat surface. That's what is texture. The profile road is no more called as profile, rather road texture. So road texture would have the valleys and peaks will be in micrometers and and small centimeters at the max. So if such kind of wavelength is there, then your excitation frequency would be very high, and you would see that the displacement transmissibility would be in fraction. Instead of 1, I would have fraction value or the 0 value, close to 0 value. That would give you good ride. So that's what you should understand from this diagram. And then you see on the face other side, irrespective of the damping, at resonance, we have seen that you have your phase angle is 90 degrees, but now it is no more of the case because it's not phi. Please do correct it in the textbook. This phi is different, and I was retaining the same phi, and this is phi minus alpha. So what is plotted here is phi minus alpha according to what we discussed, and its variation with frequency ratio. It's variation with the frequency ratio, right? And see this difference. So it is not having 90-degree phase difference at omega at resonance state. So you have your smallest value of damping you have here. It goes like this 180 degrees. But you see higher the damping, your phase all comes closer to 90. At asymptotically reaches to 90. That's what is the difference, right? And this is what you should remember. So the 2 points to be remembered here is you have x by y equals 1 when this value is very smaller than this, and x by value is equal to 0 when you have excitation frequency more. And this is the requirement of the road. That is why the asphalt road on highways are with the high frequency exciting roads. Right, there is no road profile, but still you could see on a road surface the waviness of your vehicle. At that time, you see when you are driving at high speeds, your vehicle would appear like kind of bouncing that you would experience, right? So look at both the graph, and importantly here again you look at this point, like in this case all passes through the 90 degrees, and you see this transmissibility irrespective of the damping present in your system. The damper is the part of your suspension, whatever may be the damping coefficient of your suspension. If your R value is equal to root 2. So what is that? It's omega by omega n. Again, you are going to have this one value, right? So your R value is omega by omega at resonance. It's not at resonance. R value, omega by omega n value is root 2 value. That's 1.414 value. You would have again transmissibility 1. So that can be evident and easier how that is going to be 1. Looking at your this equation. So look at this equation. So when x by y can be 1, when I put zeta, for zeta value equal to 0, it will be what? Zeta value is equal to 0, this is 0, this is 0. And here this 1 by r square, right? The zeta value is 0, x by y is that. That is for an undamped. Damper is not present, you can see. Instead, if I put r is equal to 0, r is equal to 0 means zero frequency excitation, degenerate system, right? So omega is 0. That's what. When r is equal to 0, this 0, this 0, this 0, that's 1. That's what in the graph you see. When r is equal to root 2, also you have this x by y equals 1. How? You can just take this value is equal to 1. And then just to work out, you would have this value. So cross multiply, it's going to be 1 minus r squared whole square plus 2 zeta r whole square on that side. And this side it is 1 minus 2 zeta, 1 plus 2 zeta r whole square. So this goes off. So this is square. So 1 minus r squared is equal to plus or minus 1. So let me take minus 1 value here, minus 1. So r squared is equal to 2. So r is equal to root 2. So when r is equal to root 2, this value again is 1. That is what very clear. So again, you see that is not going to be function of zeta. Any value of zeta you substitute here because that goes off here this term. You have again that one value. That is why this graph, when you plot, interestingly, you get all this variation of x by y displacement transmissibility as frequency ratio for any chosen damping would cross this point, and then it goes right. So this is all the important observation of this variation, and I have just to put these two together. This top one is for base excitation. This is for base excitation. Again, harmonic base excitation, and this is for an external excitation. So if that is so, you have to understand both the thing. And tomorrow on Friday class, we will see another interesting aspect, what is called rotational. There is an eccentric mass placed in a rotating element that would cause a vibration, and that we would see in the last class, right? In the next class. So maybe that would be the last class for the module 1, and then we will get into our vertical dynamics part. Of course, already it started. Now, whatever you are learning, this force vibration should relate, connect to what we are once again going to discuss in our vehicle dynamics course. And I have uploaded all the notes so far. What is the class notes in our Microsoft Teams? And I said that I would upload only after that you finish your submission. But first time for this module alone, I have uploaded. In case anybody of you have missed or you are not understood, you want to look at the PDF part of my lecture, that's available in MS Teams now. Please go through it. You would have got now 10 o'clock. You would have an assignment, first assignment, digital assignment, uploading module 1, and that would be till Friday. You would have a time. So everyone should upload your class notes. It's an individual submission. So as I complete modules individually, I would ask everyone to upload, and that assessment, the seriousness of your learning is what is going to fetch you digital assignment marks. So with that note, let me stop today's class, and we'll meet again on Friday. Stop recording.